from the beautiful studios of Way Happy. This is Mr. Meyer and 11.5 Measures of Central Tendency. Now, some of this stuff you have done a ton, so that will make you happy or way happy. And like mean, median, and mode. So remember the song. Mean, median, mode, mean, median, mode. Mean is the one you add up and divide. Median's the one in the middle of the line. Mode is the one you see mode at the time. Mean, median, mode. All right. Now, with that being said, let's go ahead and find the mean, which most math people will call x bar. And it is where you add up and divide all the numbers. So I am going to add them up 3, 0, 2, 0, 1, 1, 2, 4. And whoops. And I'm going to divide that by however many there are 1, 2, 3, 4, 5, 6, 7. So let's see what we got 3, 4, 5. I can't read 6, 7, 8. 9, 10, 11, 12. So 12 sevens, which is what? 1 and 5 sevens, or approximately equal to, let's see what 12 divided by 7 is. It is a 1.714. So that would be what is called our mean, right? That is the mean of the data. You might be curious about that because you want to know, right, where the middle of the road is if we added them all up and divided. That's just something people would be very curious about. All right, what about median? Median is where you have to put them all in order. All right, so got to put them in order. So we got a 0, we got a 0, we got a 1, we got a 2, a 3, and a 4. Let me make sure I have 7. 1, 2, 3, 4, 5, 6. Okay, we're good. And then, you kind of throw out the high and the low, and you keep doing that because you want to see what the middle score is. No, it's a 2. So that is called your median. Your median is 2. Now, if you have two medians, then you add them up and divide by 2, or you take the mean of them. So that is called our median, our middle number. I like that one. I like that throws out, a high number and a low number and kind of tells me what the middle person is, or the middle. Like I like it for housing prices where you throw out the big expensive houses and the cheap houses, and you keep doing that until you get to all the houses stripped down and you tell me which one's the median price. I like that. All right, the mode is the one you see mode often. So in this case, we have two modes. So that would be called bimodal. So you at least have to repeat once to be a mode. If nobody repeats, then we just say no mode. But if they do repeat, then you see which one repeats the most. And if you have a tie, like we do here, then they're both the modes. So the mode would be 0 and 2. So I would take both of those numbers, and they're both my answer. All right, that's mean, median, and mode. Let's keep moving. Like, what is one of my favorite things to do is get an expected number. So in math, we may have a bunch of statistics, and then we want to predict what's going to happen, right? Playoffs in basketball and hockey, you can look at the course of history, how many games playoffs have gone for a team or the entire league, and you can predict how many games a series will go. And here, this is Amy Musa was out shooting 3-pointer, or I'm sorry, 3 free throws. I let her do 3 free throws, and then we kept track. And this is what happened: 3 out of the 20 times she missed them all. 3 out of the 20 times she only made one. 1 out of 5 times, or well, you would get a common denominator. So 4 out of the 20 times she hit 2, and 10 out of the 20 times she made all 3. So if she were to now say, I'm going to shoot 3 free throws, what would her expected value be? What would we expect her to get? Most likely, according to this data. Well, the way you do expected value is you take the value of what it is. So in this point, not making any, and you multiply it by its probability. That would be the expected value. And you're going to just keep adding that to each one. So making 1, she noticed 3 out of 20 times, and making 2 was 1 out of 5 times, and making 3 was 1 out of 2 times. And that would be what's called expected value. You take the value that you're looking for, in this case, the number of free throws that she makes, multiplied by the probability, and you add them all up. So what is that? Well, that's easy. 0 plus 3/20 plus, what is that? That's going to be 2/5. All right, I'll do it in the next step. And that's going to be 3/2. And now I'm going to go ahead and do 3/20. Now I'm going to multiply this one by 4. So 8/20. Plus I'm going to multiply this one by, what am I multiply? 10. 30/20. So what do I get? 38, 41/20. 41/20ths or 2 and 1/20th, which is what, 2.05? That's how many I would expect her to make. So if for some reason we're like, hey, if we were a casino, we would say, all right, if you make more than two, you win, and less than two or less, I win. And then that's what the casino would say. Then you get to gamble and see if who wins. And we would probably break even if we did this 20 times because we see the statistics of what happened. All right, now that is expected outcome. You always want to think expected outcome is the outcome multiplied by the probability, and you add them all together for all the outcomes and see what you get. All right, let's take a break right there, and I'll be right back. All right, nice work. Now let's talk about another thing you may have seen in the years that you have been doing your math. It's called a box and whisker plot, and it works really good with data. It's a visual to give you an idea of what this data looks like and where all the numbers are. It involves the median, really. So you have the minimum and the maximum. Um, if you subtract those two numbers, by the way, that's called the range. If you're ever curious what the range is, you will find the median of your numbers. You will find then that'll cut the data in half. So like right here, it'll be cut in half and you'll have 50% on this side and 50% on that side. Well, then what'll happen is you'll cut that lower half in half again, and you'll cut the upper half in half of all their numbers. And what should happen is you should have 25% of the data here, and 25% of the data here, and 25% here, and 25% here. So we can see where all the scores are depending on how big and stretched out the data, the graph is. And so that is what a box and whisker does. It gives you a nice visual of kind of looking at your data and seeing how it's laid out, right? All right, so let's do these down here. Example 3, I already put them in order because using medians, we know we have to be in order. So this one here, I'm going to take all those numbers and I'm going to make a box and whisker plot and find what's called the interquartile range, or the IQR, and that is the quartile 3 minus quartile 1. Just a little heads up, or the parts that make up the box. All right, so I put them in order. Remember, you want to go low to high. And now it's going to be a little harder, so I'm going to cross out 2 lows and 2 highs. I'm going to cross out 2 lows and 2 highs. And it looks like 7 is right in the middle. So that is our median. Now remember what that's done. That's chopped the data in half. So now you have a lower half, which you want to find the median of that. So the median of this set of numbers is going to be right here, 5.5. Remember, if you have 2, you add them together and divide by 2. Same thing here. We're going to take this data. We're going to find this median, which is going to be right here. And I'm going to call that 8.5. Now, we call this Q1 and we call this Q3. And we are now ready. That will help us, by the way, find the interquartile range, which is just 8.5 minus 5.5, or 3. That's your interquartile range that it asked for. But now let's do the box plot. Now what you want to do is you want to start your data with the lowest point, 4, and you want to keep going in good tick marks, 5, 6, 7, 8, 9, 10. That was as high as I had to go, 10, because 10 was my highest point. So here is my data from 4 to 10. All right, and then I'm going to put the median on there, which is 7. So 4, 5, 6, 7. Here's our median. And then 5.5 is our Q1, and 8.5, so that was 7. 8.5 is our Q3, and that makes our box. And this is our box and whisker plot. And look at how beautiful that is. Our data seems to be spread very evenly, right? With 25% of the people being in the lower quartile and then 50% being below the median, and 50, which makes sense because they should. But notice none of the boxes like skewed, none of it's pushed together real close, and a bunch of numbers are crammed in there. These people, this data is kind of spread out all over the place, so it's not settling in on one certain spot. So that's kind of nice, and that's what a box and whisker plot looks like, and the interquartile range. All right, what about the big bully? Are you ready to find? Oh, I kind of skipped over it. Sorry. Finding the variance and the standard deviation. So standard deviation is really helpful in letting me know how far apart, if I don't have a picture, how far apart or how spread out the data is away from the mean. And so here are the steps to finding what we call standard deviation. You first find find the mean of the data. Then you subtract the mean from every one of those data values and you square it. Then you find the variance, which means add up all the squares and divide by the number of values you have. So kind of find the mean of all those squares. And that's called the variance. And then finally, you find the standard deviation by undoing the square you did by square rooting it. And maybe you can think about why you would square it. Like, why not just add up the differences and see what you get? Right? Why wouldn't we just do that? Why would math people decide to change it and square it and then add it up and then square root it? Right? Where's the logic in that? Is this just crazy or does it have a reason? So here's my list of numbers, and I am going to go through and I am going to have to, this is usually a pretty painstaking event to do by hand, and then I'll show you on the calculator. But I see 4, 5, 6, so 4, 5, 6. I see another 6. Is this the same data set, come to think of it? 7, 8, 8, 9, 10. 7, 8, 8, 9, 10. That is feeling very similar to the one we just did. 4, 5, 6, 6, 7, 8, 8. And yes, it is. So what was our, we never found our mean. Bummer. All right, so here comes our mean, right? Add them up and divide by how many there are. So I guess I'll use virtual Sheila. She's kind of in the way here though. So 4 plus 5 plus 6 plus 6 plus 7 plus 8 plus 8 plus 9 plus 10. Sheila says it is 63. And how many numbers do we have? 1, 2, 3, 4, 5. Yes, 9 divided by, divided by 9. I guess I already did it in my head, is 7, or at least tried. X bar is 7. Wait, I shouldn't put that there. It's going to be annoying. X bar is 7, the mean. So now realize what the rule was. These are all the x's. So now what we have to do is take the x's and we got to subtract off x bar, right? And square it. Crazy. So here we go. 4 minus 7 is negative 3, squared is 9. 5 minus 7 is negative 2, squared is 4. 6 minus 7 is 1, squared is 1. That's also going to be 1. 0. Now 8 minus 7 is 1, squared is 1. And that would also be 1. 9 is going to give me what? 2, 4. And 3 is going to be 9. And that is our squares. Now we can find the variance. The variance, remember, they label it like this. Variance is this fancy curly O, and it's where you add them all up and divide by how many there are. So what is that? 10, 15, and 10, 50. That's 30. 30 divided by 9. So our variance is 30 over 9. If you want, I can find that on my calculator for you. 30 over 9 is 3.333. I guess we knew that. And that's called our variance. So they asked for find the variance. They said find the mean, did it. Find the variance. There it is. If they asked, I don't think they did. And then find the standard deviation, which we'll just do one of those because we're going to square root that number. It's going to be the square root of 30 over 9 or root 30 over 3. Or what are you going to call it? Raise it to the half power is the same thing as square rooting. So 1.83. 1.83. Now, the neat thing about this is that it kind of tells you there's this curve, right? And we would normalize this in statistics, but here we're just going to talk about what it is. The mean is 3.3. And if you go up 1.87, so one standard deviation up, you pick up like 68% of the data. If you go up just 2, it's like 90 something. I want to say 95%. If you go up 2 standard deviations, you go up 3 standard deviations, so you add 1.83 3 times to our mean, you'll get like 99% of the data. So that's what standard deviation is. Kind of tells me how far I go out to pick up all the numbers. And that's what standard deviation is. All right, let me ask you one more question and we'll finish this up in a minute. All right, nice work again. Now, let's talk about outliers. Outliers can mess up your data a little bit. If you have all this data and you put it in, you look at it, there might be, 1 or 2 that are too high or too low, and they're kind of no good. Like maybe something bad happened when you measured that. Maybe it was a house in Livermore. We're looking at all the houses and we got this one that's just ridiculously expensive. Maybe it's just, on bajillion acres of land and we should throw it out because it doesn't really count with all the other houses in the same area, or whatever. So here I have an example. And how do you find those outliers, and what should you do if you find one? And what you do is you take it out. If you have an outlier, just take it out and redo the data and see how it's changed. So here you go. An outlier can be found if it's 3 or more standard deviations away from the mean. So if somebody's 3 standard deviations bigger than the mean, X bar, then toss them out. So look at all that data. Those are can heights in millimeters, because our factory is cranking these things out, and we want to make sure that our can heights stay consistent, because we don't want to have funky cans. All of a sudden, stacking them is going to be a mess in the stores and stuff. So we got to make sure that we stay very consistent. And here they are. We measure them all from a group. We're like, all right, let's see how things are going. Now I said I would show you on the calculator. So here you go. Virtual Sheila, I got it on. There's a stat button right here in the middle. So what I want you to do, right by the 4 arrows, I want you to just hit stat. And the very first thing is you want to edit your statistics. So we're going to hit edit. And you're going to see some lists. Now, I already put all those numbers in list 1 because that takes a little bit of a while. So you might want to do that too. But if you have stuff in it like I do in list 2, make sure you hit clear, not delete. Delete clear deletes the list, while clear will clear it out. So you might want to clear out your list. You hit clear, you hit enter, boom, it zaps the list. And then you can start typing. So in list 1, why don't you copy that chart and put it all in? All right, now that we've done that, we're going to go ahead and we're going to hit stat. And we're going to go over to calculate. And the very first thing, one variable statistics, we're going to hit that. And it's going to maybe ask you some questions or not. You'll just hit enter. It's asking me if it's in list 1. And I'm going to say, yes, it's in list 1. And I'm going to calculate it. And boom, there you go. You got your X bar, which is your mean, 92.77. You got your standard deviation down there, which is 0.194. You got N is 15, which means there's 15 numbers in the list. You got, keep scrolling down, you got your minimum is a 92.1, your quartile 1 is a 92.7, your median is a 92.8, your quartile 3, you got your maximum, so you can find your range. You got everything you could possibly need. So what did we need here? Well, we have that the mean is 92.77. So we have X bar is 92.77. And the standard deviation, I already forgot, was something gross 0.19, I want to say 0.195. Now, the question is anybody 3 times bigger or 3 times smaller? So how do I tell? I just come over here and I go 92.77 plus 3 times 0.195. That's 3 times the standard deviation added to the mean. Is anybody bigger than 93.3? Look through our list. No. So don't worry about it. All right, what about taking this guy, right? And doing the exact same thing. I hit second enter. I'm going to change that to minus though. I'm going to hit enter. 92.185. Is anybody smaller than 92.185? Yes. This guy right here, something's wrong. So now maybe we'd have to find out what machine cut that can, and we want to find out if that's happening a lot. I mean, that's messing up stuff, and people are wondering why their can's a little smaller than usual or whatever. But we want to see what it does to our data. So here was our data with the outlier. And now I'm going to just go back to my calculator and I'm going to say stat. So where's stat? And I'm going to go to edit and I'm going to go find that 92.1, wherever that thing is. And I'm going to take it out. There it is. I'm going to hit delete. Boom. Now I'm just going to go over to stat, calculate one variable statistics, and I'm going to hit enter. And look what we get now. The mean is 92.8 and the standard deviation is 0.07 or 0.08. So we go 92.8, but 0.08. That's crazy, right? Our machine is much more accurate, right? All our machines are much more accurate. The mean didn't change too much. And that's good because the outlier didn't have too much effect there. But look at the standard deviation. That means everybody's really clustered around that mean. They are not spread out, so there's no weird can heights. And that's it. Have a great day, and I'll see you tomorrow. Stay happy.